Okay, so this is our final section, and I'm just going to talk a little bit about some of the things we can measure with kinematic analysis, what they would look like, give you an insight into what we may be doing in next week's lab, and get you thinking about what you might want to do if you want to use kinematics as part of your group project. So gait, we started in our first week talking about gait analysis, and it's always an easy one to go back to and use in our minds to try and visualize the types of variables we might measure with motion or kinematic analysis. Position, when we're thinking about a person's gait, it might be their position of their center of mass, how high it is off the ground, how much it undulates or moves when they're walking or jogging or sprinting. Because a lot of the times that's related to running efficiency, where a lot of bounce or a lot of movement in the height of the center of mass could be linked with a less efficient running pattern. Obviously, joint angles are quite important. When we talk about running, a lot of the time the angle of the feet and the knees is very especially linked with injury. A lot of modern proposals talk about barefoot running, forefoot running, landing on the mid or the forefoot. So the angle of the ankle at impact, which directly relates to the angle of the knee, has been in some bodies of literature linked with decreased risk of injury, and is commonly seen in middle to long distance runners. But if you think about a sprinter, they're also very much up on their toes. So someone will definitely land with a different ankle and knee angle if they're running faster. Distance. Remember in our first class we measured stride length just by counting the number of steps along with the speed I was walking on the treadmill. Obviously we can also measure this by recording the distance the center of mass of the athlete moves during their stride and calculating that from our video. Any of these associated positions can also be translated into velocity and acceleration. Or simply looking at time, contact time, flight time, all key factors in the deterministic model for sprinting, running, or walking. So to give you a little bit of insight into a research project I undertook when I was last a staff member at Northern Michigan University. When I was here in 2012, I worked with Dr. Drum and one of our undergraduate students at the time, Mitch Stevenson. We travelled to Texas in February 2013 and we collected data on the running gait of ultramarathoners. This is the route. It's a 100-mile course, which was completed on 5 20-mile loops. This is what the trail looked like, a mixture of single and double track, but we were located on a double track section. We measured some key performance variables to see how they changed across the race. When the runners came in front of our camera, we measured how fast they were going in meters per second. And we can see that they slowed down each lap as they came through the race. We also looked at their stride length, and interestingly, we can see a very similar pattern here where their stride lengths became shorter, which you would propose may be linked with why they got slower. A factor that didn't change significantly was their stride rate, how quickly they turned over their strides. So they were able to maintain the rate at which they took their steps or their strides, but not the length. In terms of how they struck the ground, we can see the majority of our runners were either rear foot strikers. We had no forefoot strikers, and everyone after lap 3 was a rear foot striker, so landing on the heel strike. The blue bars here tell us the number of runners, so everyone, 100% of the athletes were running on the first lap. This dropped to 80, 55 and around 30% by laps 4 and 5. Again, in red we can see the number or percentage of participants with a mid-foot strike. So in laps 1 and 2, we can see any of our runners that were running had 30% or 1 in 3 of them were landing on the midfoot. the rest were landing on their heels. And this dropped dramatically in laps 3, 4, and 5. So that's just an example of maybe some type of research that was conducted in the field by professors in your own department. And that has been published at a conference, and we're currently in the final stages of getting it out in print as a journal article. So in terms of the data we take from Kinovia next week when we analyse it, we will bring it more than likely into Excel. But there are many other advanced software options that as graduate students here you would be exposed to and use in some of your lab procedures classes or possibly as a thesis project. So we'll talk more about the analysis when we get some data next week. And we will be working on your Excel skills from next week onwards. So if you haven't used Excel in a while, I would recommend a refresher. And I'll put up some resources on Educat to kind of get you started and with some simple activities to do to get you more familiar with Excel, and we'll start working more with that from next week onwards. If you do have any questions, please post them in the Facebook group. I'll be happy to answer them there, and everyone in the class will be able to benefit from the answers. Hopefully you've enjoyed this video series. Is given you the knowledge you need to do kinematic analysis, and we'll have plenty of time in class next week for some hands-on work.